So, welcome to lesson 4.5, which is the final lesson in this module on cultures and civilizations, and is going to be a very short lesson about cosmic civilizations. So, when we were looking at the topic of periodization in module 2, we considered Kardashev's scale or typology of cosmic civilizations. So, let's write that up again. So here is the Kardashev scale. A type 1 civilization controls the resources of an entire planet. Type 2 controls the resources of an entire solar system, and type 3 controls the resources of an entire galaxy. And then that was Kardashev's original scale. People have considered extending it, say, to a type 4 civilization, which would control the resources of an entire galactic supercluster. So not just one galaxy, but this civilization controls multiple galaxies. And then step 5, one could possibly go up to even bigger collections of galaxies, or maybe step 5 is just to control the resources of the entire universe. Now, one of the problems with this scale is that it doesn't take into account the fact that as technology develops, it becomes more efficient in its use of resources. So, for example, smartphones have become, if anything, lighter, smaller, more compact as they have become more capable. So the technology has advanced, but its use of resources has decreased. So measuring civilizations in terms of their use of resources may not be the best method. Though that said, I think this scale gives us a fairly good intuitive grasp of the issues that and although there may be sort of nitpicking about whether controlling the amount of resources is the most accurate measure, nevertheless I think we could tell the difference between a civilization that controls a planet but it has not gone beyond the planet versus one that is zipping around its solar system from planet to planet. And we could tell the difference between that and one that has cracked the problem of interstellar travel and so is moving on to other stars. So I think it would make sense that these are definitely steps up in technological capability. And then the question is, where are we now on this scale? So where is human civilization at the moment? And people have put forward various estimates, typically ranging from about 0.3 to 0.7. We're clearly less than 1 because we haven't we certainly don't control the resources of an entire planet. Now, I would say that since humans don't control the resources of the ocean by any means, it's said that the bottom of the ocean, or we know less about the bottom of the ocean than we know about the surface of the moon. So the ocean is a mystery to us. That's 3/4 of the planet. So I don't think we can say we're up here at 0.7. It would make more sense to say we're down here at 0.3, even if that. And people have suggested ways to try and make this scale more quantifiable. So one suggestion is to think about it in terms of energy consumption. So we know how much energy is available on the planet for Earth. It's basically the amount of energy that reaches us from the sun, and we can work out, we know how much that is. And that is what drives everything that happens on Earth pretty much. I mean, there is some energy comes up maybe from radioactivity or something in the Earth's crust, but mostly it's the energy we receive from the sun. And we know what that is, and we also know how much energy human civilization processes. So we can compare the two and give a quantitative number for where we are. But again, that doesn't take into account the fact that as technology advances, it becomes more efficient in its energy use. So the energy scale may again not be really give an accurate figure. So we can think about this as a kind of qualitative description of civilizations, but at the moment there isn't really a quantitative interpretation of this that people would agree on or find satisfactory. Now the question is, are there actually other civilizations in the cosmos besides our own? So are there other civilizations? Well, the Russian theoretical historian Alexander Panov says that yes, there very likely are, because he has an argument that life cannot be seen as something that just happened on Earth. It must be a galactic phenomenon. So it takes a galaxy to produce life, is his argument, which we'll see in a moment. So life is a galactic phenomenon. It's too complex just to emerge on a single planet. And what he says then is, supposing we draw a timeline here, so that's 5 billion years ago, 4 billion, 3 billion, 2, 1, to today. Billion years ago. Then, as far as we know at the moment, Earth is about 4.5 billion years old. So Earth came into existence then. That's how old the planet is. And then life seems to have emerged pretty soon after that. Let's say, to be conservative, 4 billion years ago, though some arguments is, it was only about 0.2 billion years after that. But let's say we'll put it at 4 billion years ago. So that's when life, the very simplest forms of life, emerged, bacteria. And then after that, their next big stage was around here, where the first forms of life with cell nucleus emerged. And then it was around here that the Cambrian explosion occurred, which created all the basic forms of life that exist on Earth today. And then around here came the dinosaurs, which dominated the Earth for a while. And then it was around here that the mammals came. So what he points out is that we can see that the major stages in the evolution of life have taken increasingly shorter times. So it took a long time to do that, then quite a long time for that, but then it's coming at an accelerating rate. And he says then there's something rather anomalous about this. If it took so long to get to the next stage there, how come life, which is the biggest step, the most fundamental step, seemed to have happened in such a short time? He says this doesn't make sense. The development of the basic biological models, molecules, DNA and RNA, must have taken longer than this to fit in with this general pattern. So there was a prebiotic evolution as these complex biological organic molecules emerged. And he says this must have taken longer than that. So it can't have just happened on Earth. So it must be that we project it back, and he estimates by assuming the same kind of, he fits these to a curve and show that they lie on a curve. And so if he extrapolates back, he finds it comes to about 9 billion years ago. That is what must be the true duration of prebiotic evolution. So there was a roughly 5 billion year process before life emerged, and it happened to, we know it emerged on Earth, obviously, but he's then saying that this prebiotic evolution must have happened elsewhere in the galaxy for a start. And so if we draw our galaxy as the galactic center, and it's rotating around, we know that the galaxy rotates at it takes 0.2 billion years to complete one rotation, and yet we're saying that life took 5 billion years to emerge. So these organic molecules were being evolving somewhere in the galaxy, and that took a process of 5 billion years, which is a lot longer than the time for the galaxy to rotate. And we also know that due to meteorite impacts and supernovas, when molecules were evolved in one part of the galaxy, they would occasionally be spread to other parts of the galaxy, as I say, because comet impacts could throw off debris that then would go into interstellar space and drift through the galaxy and arrive on other planets. And so we can think of the galaxy as like a pot that's being stirred, and it's being stirred a lot faster than it's taking for life to emerge. So in the time that life emerged, the pot was stirred 25 times, because 0.2 goes into 5, 25 times. So the pot was well stirred with these organic molecules, and some of them happen to arrive on Earth and produce life here, but because the galaxy has been well stirred, these biotic molecules must be on all sorts of planets all through the rest of the galaxy. And so life did not just emerge on Earth, it emerged in the galaxy and is going to be all over the galaxy. That is his argument, and suggests therefore that, well, we can assume that life certainly exists on other planets, and it seems not an unreasonable inference that then some of them may have given rise to civilizations, just as has happened on Earth. Now the next question that arises is, if there are these cosmic civilizations out there, how many are there? Or at least, how many are there in our galaxy? That's what concerns most people, since those are the ones that will be reasonably accessible. And a way to answer that is the Drake equation, developed by the astronomer Frank Drake in 1961. And his equation says that the number of civilizations capable of communicating, that's what he was particularly interested in, not just the number of civilizations, but the number of civilizations that we could actually communicate with, because he was a radio astronomer looking at radio signals coming from outer space, trying to detect extraterrestrial intelligence. So he wanted to know, what are the chances of me finding any? How many are there going to be out there that I could expect to detect? So this is the number of civilizations that actually are capable of communicating with other ones. So he said that's the number is going to be, firstly, the rate of star formation in the galaxy, the number of stars coming into existence per unit time, multiplied by the fraction of those stars that produce planets, FP, multiplied by, for each star that produces planets, the number of planets it has that are capable of supporting the existence of life, NE. And then for each planet on which is capable of supporting the existence of life, we need to multiply by the fraction that actually produce life, FL. And then for those that produce life, we need to take into account the fraction that produce intelligent life, Fi. And then for the fraction of intelligent species, how many of those actually end up producing civilizations that are capable of communicating across the galaxy, Fc. And lastly, we need to multiply by the lifetime of a civilization, L. So he assumed that civilizations would only have a finite lifetime. They might go extinct after a while. So they're going to be coming and going. So stars are being produced, and they're gradually producing these civilizations which are then going extinct. And if you put in numbers for all these things, you can work out how many are going to be in existence at a particular time. And those are the ones that we can attempt to communicate with. And people can, come up with different estimates for these various factors. And some people would be more optimistic, some more pessimistic. And the range of answers, depending on whether you're pessimistic or optimistic, is between about 20 in the galaxy to as many as 50 million. So here they'd be very rare, and radio astronomers would really have a really tough time finding them. Here they'd be pretty common, and you should expect it wouldn't be too difficult to find civilizations to communicate with. And when in developing this equation, Drake wasn't really trying to produce an estimate because it is all guesswork, but he was trying to bring out what the factors are so that we can sort of have an understanding of what we're dealing with, and it might guide strategies, as to where to concentrate effort, for example. Now, Alexander Panov, who we just saw his idea that the evolution of life is a galactic, not a planetary phenomenon. He said that problem with this Drake equation is that it doesn't take into account the fact that it takes a while for life to emerge. So it's assuming a steady state situation. But when the galaxy first came into existence, at first there was stars might be being produced, but there was not going to be any life on them because it takes a few billion years for life to be able to emerge at all. So he said we need to take that into account, and we also need to take into account the lifetime of stars, because stars too, go extinct after a while. So he developed a model that took these factors into account, and he found that the number of civilizations that can communicate, this n, actually goes in a kind of pulse and then decays to this steady state. So this is a steady state described by the Drake equation, but this pulse is because the galaxy gets started and then life emerges, and at that point civilizations are going to be created all around the galaxy. So at that time, a certain amount of time after the galaxy started for life to emerge, then these civilizations will all kind of emerge together. But then as time goes on, you'll fall back into this steady state as some are going extinct and others are being produced. Then the Drake equation starts to apply. And in terms of numbers, he found that it was up here at about, well, down a bit, because the peak here was at about 1,000, and the steady state here was at about 300. So I don't know if I got that in the right place, but that's about 300. And this is over time. So the peak here occurs after about 10 billion years. And so that would be, say, about 15 billion years there. 5 billion here. So that's 10. This is billion years. And the galaxy is thought to be about 13.6 billion years old. So we're currently there. So we're kind of a bit past the peak, but we're not fully in the steady state part yet. So it's kind of, good news to some extent that there's a bit more. We should expect there to be a few more than the Drake equation predicts. But Panov then says, he doesn't completely go along with that, because this assumes that civilizations develop in complete isolation. But he suggests that when they start communicating with each other, they're likely to be able to help each other and extend their lifetimes. So this is a lifetime a civilization might have. If it is just developing in isolation, it comes into existence and then goes through its history and becomes extinct after a while. But when they're interacting with other civilizations, they can kind of share knowledge. And if one civilization is going through a bad patch, having problems, another civilization can help it. So when civilizations are communicating with each other, we should expect their lifetime to increase. And so he develops another model based on that assumption, and he gets a different kind of chart. So let's draw that. Okay, so this is what Panov finds with his idea that civilizations can help each other out and extend each other's lifetimes once they start to communicate. So up here is the number of civilizations, and this is now a logarithmic scale because it varies a lot more than with just the simple assumptions. So this is a logarithmic scale, 10 to 1, 10 to the 2, 10 to the 3, up to 10 to the 5. And here is the civilization formation rate. So, with the Drake equation and this assumption, civilizations are being formed all the time, and they're also going extinct all the time. And it's the balance between those two, or when those come into a steady state, that determines the number of civilizations that are going to be in existence at any one time. And as we said, with the Drake equation, you're just considering the steady state. But Panov, taking into account the evolution of the galaxy, shows how there's an initial pulse, and then it goes into the steady state mode. Well, but now we're assuming that civilizations can be forming at a certain rate, and that when they interact, they increase their lifetime. So because they have a longer lifetime, there'll tend to be more civilizations around than there would be if they weren't able to help each other out and make each other last longer. So it's a curve. We kind of recognize this from the mathematics module and work we did on critical transitions. It's a curve with some hysteresis. So let's just talk it through. So when the civilization formation rate is fairly low, there will be just a few civilizations in the galaxy, around about 10, say here. But as the civilization formation rate increases, then the number of civilizations that are around will naturally increase. So with a higher civilization formation rate, it'll keep it at a higher level, even though some are going extinct, but they're coming in. They're coming into existence at a faster rate. So the number around at any one time will tend to increase. But then, with the assumption that once they start communicating, they can extend each other's lifetime, when the civilization formation rate is large enough, and the exact figure that Panov calculates is 1.35. At that point, there's a sudden jump, because now there are enough around to communicate with each other, help each other out, and make themselves last longer. So they hang around a lot longer. So although the civilization formation rate is constant here, the civilization extinction rate is now much decreased because of this interaction and ability to help each other. And as the civilization formation rate then increases further, it will now be on this curve, and the number of civilizations will just gradually increase. And but then if the civilization formation rate decreases, it's going to come back here. But in line with the theory of critical transitions that we studied, this hysteresis, it doesn't switch back to here because it's now in this higher steady state. So the civilizations are in touch and they're able to make each other last longer. So they won't jump down to there, they'll just keep decreasing in number slightly as the civilization formation rate declines. But we then get to the next critical transition. At this point, the civilization formation rate is now not high enough to keep enough civilizations in communication with each other for them to be able to help each other out. So at that point, they become isolated again, and so the number of civilizations will plummet. They will now only last that default lifetime rather than the extended lifetime from communication. So with not enough civilizations around, because there's not enough civilization formation rate, this drops down to isolated civilizations, and so the extinction rate has drastically increased, and so it's at a low, finds equilibrium at a lower level. And so as the civilization formation rate decreases further, it will go down here, fall back down here gently. So that's fine. You know, we can imagine that idea then, that civilizations, if they're forming fast enough, create actually more than we might expect from the Drake equation. But Panov suggests we also need to, tie this to this. So he said that there's a pulse of the civilization formation rate. When you get to that point where life is able to come into existence, it creates that pulse. So we can see that the pulse tends to increase up here to 1,000, which is here the 10 to the 3, 1,000. So he suggests that this is actually the history of the galaxy is going to be like this, with this pulse here, that the galaxy has evolved like this to here. And with the pulse, it got up to 1,000 here, so it did get up to here. And with this pulse of galaxy formation, it would have gone up that curve a bit. But now we are moving back down here. And we said that the steady state was at around 300. Well, by his calculations, assuming the galaxy is 13.6 billion years old, we're around here at about the 500 level. And it's actually at the 500 level that the transition occurs. So we're either there or we're about to go over that critical transition, and then to a much lower number of civilizations in the galaxy. So it's an interesting question, precisely where are we on this curve? But the fact that we don't really see many civilizations suggests we might have gone past that critical transition, so we've kind of missed the boat. There was a time in the galaxy when it was very active, full of civilizations, but it's now fallen back due to this process beyond that critical transition, and there's now very few civilizations in the galaxy. And that brings us to the idea of the Fermi Paradox, which says that if there are other civilizations out in the galaxy, where are they? Because you know, our civilization is, let's say, well, it depends where you want to start, but if you start, say, with the invention of agriculture, we're 10,000 years old. And we have reached a pretty advanced technological level. We've, you know, landed on the moon, and we've, you know, got artificial intelligence and so on. So we've got pretty far in just 10,000 years. But some of these civilizations could be 1,000,000 years old. You know, compare 1,000,000 to 10,000. A civilization that's 1,000,000 years old, you'd expect to be vastly more capable than us. And so we would expect to see the signs of them. You know, they would be, their rockets would be moving through the galaxy. So when we look out at the galaxy with our telescopes, we won't just see stars, we should see the exhaust of their rockets, you know, zipping through the galaxy, or we should certainly see some signs of them. And we would also expect them to have found us, because, you know, if they are capable of the technology that's 100 times what we've achieved, you'd certainly expect them to be able to detect life on other planets, and then to have come here and, you know, said hello. But we don't see anything. We don't see anything at all. As we look out into the night sky, it's just natural. There's no sign of intelligent life, sign of civilization out there, and we don't seem to see any sign of aliens having visited us here. You know, Eric von Daniken and so on notwithstanding. So that is the paradox. Yes, we would expect there to be other civilizations, and yet we don't see them. So what's the explanation? And of course, you know, there are hundreds of possible explanations people have suggested for the Fermi Paradox, ranging from you know, civilizations just blow themselves up through nuclear war not long after they reach our stage of development, and we're just about to do that. Or if you're an environmentalist, you might say they cause climate change and destroy their planet. So that's one explanation, that they just go extinct after only a few thousand years. Another explanation is that, well, they are out there, but we're kept in quarantine because they don't want to disturb our development. So they keep us isolated, like in a zoo. And then there are, you know, you could say, well, they have been here, you know, they built the pyramids and so on. My own view is that actually humans are alone in the galaxy. I take the Fermi Paradox very seriously, and I think, contrary to all this, actually humans are the only intelligent civilization. But that's just my personal view. You know, many people wouldn't agree with that, and, you know, think that no, it's very unlikely that we would be unique. If life can exist here and civilization could exist here, then it seems the natural thing to assume that it's fairly common throughout the galaxy. But you know, we just don't know because of the Fermi Paradox. We've got these arguments, but, you know, they rely on a lot of assumptions. And so we really just wait and see until either we're able to go out and explore the galaxy and satisfy our curiosity, or somebody, aliens, find us. Okay, and lastly, we're going to consider the issue of malevolent cosmic civilizations. So Stephen Hawking advised against humans advertising our presence to the rest of the galaxy. He said that it might be a false assumption that other cosmic civilizations are benign. He pointed out the negative consequences for less advanced regions on Earth when they were contacted by more advanced civilizations. And he said, you know, the same could happen if we're contacted by a more advanced alien species, or even if they're more benign than human societies have been to each other. It may be that they're just so advanced that to them we just look like bacteria, so they wouldn't even, you know, register us, and they might just, you know, take over our planet without even thinking about it. So he says, yes, by all means, listen out to the galaxy to see if you can detect signs of other civilizations out there, but don't let's send out signals into the galaxy, because we never know, who we might attract. And Alberto Caballero has tried to sort of quantify this idea of Hawking's by calculating the number of malevolent cosmic civilizations that might be out there. So his approach is to think about, firstly, the current probability on Earth here of one country invading another. So he is then assuming that the probability of one country invading another is similar to the probability of an alien species invading and attacking another alien species. So he starts with thinking about the current probability of one country attacking another. But then he acknowledges that probability is changing over time. It's believed that the world is getting more peaceful thanks to the United Nations and what have you. So countries are less likely just arbitrarily to attack each other. So he says we also need to consider how that probability is changing over time. So, it could be increasing, but he believes it's decreasing. And that's important because then, we're saying that the longer civilization lasts, perhaps the less the chance of it attacking other civilizations. So more longer lived alien civilizations will be less likely to attack us because they've become more enlightened. And then he says another factor we need to consider is the time it takes for a civilization to reach the level of interstellar travel. So it's at that point that it actually has the ability to attack other civilizations. And then lastly, he says we just need to consider the total number of civilizations. So with these assumptions, how many alien civilizations there are in total, how many of them have the ability to travel between star systems and attack other alien civilizations, and then from these things, what the probability of them wanting to do that is. So we're taking into account that some of these civilizations will be longer lived, and so their probability, or by the time they reach interstellar travel, their probability of attacking each other would have decreased to a certain level. So we can then put a number to the chance of an alien civilization wanting to come and attack us and being able to do so. And what he calculates is that there are about four civilizations are a threat to Earth. So there are 4 civilizations that are malevolent and close enough to Earth to pose a threat. That's what he comes up with, 4 civilizations. Now clearly, these assumptions are pretty hand-waving, and so we can't replace a huge amount of reliance on this particular number. But it at least is a first attempt to address the issue, and may give us some sort of general idea as to how likely this is. And 4 civilizations that are a threat, well, it sounds like then a bit of a risk. So maybe Hawking is right, and we shouldn't let them see that we're here.